This is my very first useful application using native Forth on PlasMa. If you've been following along, you'll know that I'm coming at it as a Forth novice, having been put off using it decades ago due to its perceived complexity. This video is aimed at a like-minded audience. The last time I showed the key source word reading word definitions from a tape or disk. But how do you get data onto tapes or disks in the first place without using another computer, as I did then? In other words, how do you bootstrap the system from scratch? It's easy with some Forth systems. You just use their built-in editor. But there isn't one here, so it's catch-22. How do you write an editor without using an editor? So this application is the first step in the process, something to save word definitions to a disk, such that they can be reloaded later and gradually refined into a practical editor. And before starting, just a few changes to PlasMa. We're on version 6.54, and apart from a few bug fixes, the major change is the teletype has been upgraded with cursor addressing features. It's now more like the Opera screen in Plex. There are new Forth words to read and write the current cursor position and for setting colours, so no prizes for guessing the driving force behind this upgrade. I'll set the row number to 8 and the column number to 10 and print the value 100. A minor drawback is that it no longer auto-wraps, so you have to handle what happens if the cursor runs off the end of the line or the screen. It's also worth mentioning that PlasMa's LCD screen is inherently slow. It's more obvious when clearing large areas of the screen, like TTY clear, so don't write to it too frequently if you're bothered about performance. You get away with it in the Plex emulation, as the screen is treated as an asynchronous peripheral, so your program can check its status and do other things while it's busy. But with Forth, the screen is synchronous, so you just have to wait. The other change is minor, but maybe more contentious. The branch words are now called jumps. This may not be an issue if you always use high-level if-then or do-until words, but these are not built in, and at the moment I'm quite happy sticking with simple jumps as shown last time. The only tricksy part is the use of square brackets around the offset, but this is simple and consistent, and counting offsets by hand is no big deal for small routines, especially if you've cut your teeth on machine code where you have to do it in hex. Being able to name everything in English is such a quantum leap forwards anyway, it's a minor point. So this is phase 1 of a screen editor, where you input or edit a screen's worth of Forth and save or load the screen as an entity. Each screen can be saved to a different location on disk, and you can split your application over multiple screens if needed. And PlasMa's disks are ideal for this, as there's no file system. They are just a collection of sectors addressed by a sector number. I'm going to use a buffer in memory to hold one screen, so these are the functions. Create a new screen, which saves all keyboard input into the buffer. Display the buffer, save the buffer to disk, and load the buffer from disk. The key source word can then be used later to either read the buffer or the disk. I'll start with the word for creating a new screen. It's going to run as a loop, capturing each key press and appending it to the buffer. And the key word might seem the obvious choice to capture key presses, but it's not suitable here as it treats control keys differently. So I'll use the key query word instead. And this works for any key press and returns false if no key is pressed, otherwise it returns true along with the key value. I can wrap it up in a convenient wait for key word. It will keep looping round until a key is pressed. As I showed before, the jump offsets are in bytes, and each fourth word occupies 2 bytes. So you just count in twos. So -2, -4. I want to use the escape key to break out of the capture loop, so I'll need its ASCII code. The last time I showed the char word being used interactively to print ASCII codes to save looking them up. If I do char a print, you see the value 65. But as with the key word, this does not work with control keys like escape. But we've just created a wait key word, so why not use it? We'll define a new word called k, which calls wait key and then prints the ASCII code. Enter k, press A, it's 65, so it seems to work. Try k, then escape, 27. Okay, back to the design. Define character escape is 27. Now we know from Jones 4th and other examples there are more efficient ways of defining character constants like this, but again this is getting complicated too soon. And in my view it's not necessary unless performance is an issue. Let's keep it simple. The same argument applies to allocating buffer storage. There's no need for words like Jones 4th's variable and a lot just yet. We've got 64,000 bytes to play with, so why not use something at the top of store for now, say 60,000. And don't forget this is a one-off exercise just to get information saved to disk. It can all be improved later. So we'll define screen address 60,000. Now we need a terminator character for the buffer, so key source knows when to stop. The spec says the terminator is 255 or hex FF, so I'll define that. Character end of screen 255. Okay, now for the main routine. We'll call it new screen. It's going to clear the screen, TTY clear, and put the memory address on top of stack. Just note that TTY clear clears the teletype screen and not the entity in the buffer. In hindsight, the word screen may have been a bad choice, and maybe I should call it something like block, but I'll do that in phase 2. I'm going to call wait for a key. Now it's handy to make a note of what's on top of stack at each stage while you're getting the hang of it. So we've got the address on stack, and now we'll have the key. Right hand entry is the top of stack. Now I want to test if it's equal to the escape key or not, and the test will destroy or consume the key value, so we need to duplicate it first. So we'll have A, K and K on the stack. We can now put the escape character on the stack and equals does the test. We'll end up with A, K and a boolean that says true or false whether it was the escape key or not. Now if it is the escape key, jump if not 0, we'll jump to the end. I'll fill this in later. If it's not the escape key, I'm going to echo it to the screen. So again we need to duplicate it, make a copy and emit it. Our stack will look like that still. Now the buffer address and the character are on stack, and I want to use the store character word, which is a C shriek, to write it into the buffer. And this was a good example to me of why you need to get stuck in and try coding an actual application instead of just following tutorials. It really makes you appreciate why you would need some of the more obscure words. The store character word needs the character and address to be the other way round. So my immediate thought was to just use swap, but the word also consumes both items. So I would lose the address value, which I need to increment later. And this is where over comes to the rescue. It copies the second item onto the top of stack. I can never see the point of this until now. So if we did over, the stack would look like that. The top two items, the key or the character and the address, they're perfect for the character store. So we can do that. As I mentioned, that consumes the top two, and we're left with the address on the stack. We can increment this now. 1 plus is the word that increments top of stack. And finally, we go back to wait key again. And this point is where we would end up if the escape key was pressed. We'd have A and K on the stack. So we drop the key and store the terminator. So we'll put C, end of screen. So we got address, end of screen. Now these two parameters are the wrong way around again, but this time we don't need to preserve the address because we finished. So a simple swap will do. So we've got end of screen and address. We can do the store character, which takes these two, nothing left, and we can finish the routine. Now I tried a few rearrangements on paper to factor the code into smaller, easy to understand words. Good programming practice in general, not just Forth, and decided to factor out the part that gets the key and the part that saves the key. Now these work fine, but get key really needs to handle typos. The interpreter uses the backspace key to erase the last character, and I planned adding this feature later to avoid complicating things here. But during rehearsal, Murphy's Law, as soon as the camera was running, I kept making mistakes. So we need a couple of new character codes, which you can find using the K test word just now. I won't do that, but it is the space word, the space character rather, is 32, and the backspace key is 8. And a new word to handle the backspace key, handle backspace. I won't go into the details, but it starts off with the address on stack and the key, and is going to end up with a decremented address. So we drop the key, decrement the address, and that deletes the character from the buffer. And then to delete it from the screen, one of the new words, TTY decrement column, which moves the cursor back to the character we want to get rid of. I'll then output a space over the top of it, and finally another TTY decrement column. We finished. So the get key part, get key, which is going to start with an address and end up with an address, a key and a boolean. It's going to be wait for the key, duplicate it and check its backspace, and if it is not, jump if 0, we go to the end. If it is, we call the routine we've just made handle backspace. And when we've handled the backspace, we can jump back to the wait key routine. And this is the end part. We're going to check for escape now. and that's the end. So that's the part that replaces this bit, and the save key part was this section, duplicate up to this bit. So this was get, this was save. Okay, the main routine can now be simplified. New screen. Clear the screen and put the buffer address on the stack. Get key. And jump if it's true. If the character is an escape, jump to the end. If not, save key and jump back to get key again. And at the end, as before, restore the end of screen character. Okay, I'll just work out these offsets. As I mentioned, a piece of cake really. You start from the offset itself and count in twos, forwards or backwards. So the end is here, so we go 2, 4, 6, 8. And then the get key comes back to here, 2, 4, 6, 8, 10. And that's it. I didn't do the same for this one. The get key value is very similar. Jump to the end, which is here, 2, 4, 6, 8. And this one, 2, 4, 6, 8, 10, 12, 14, 16. Now obviously if you start inserting or deleting words within these jumps, you need to recalculate the offsets, but it's relatively trivial. If you use the if-then words, you wouldn't need to do any of this, but as mentioned, this is getting too complicated too soon. You try explaining how an if-then-else or if-else-then works to somebody who's not familiar with this and their eyes glaze over, like mine did. So we'll stick with jumps. Right, I'm just going to enter these routines and see if they work. I'll type new screen. It's waiting for a keyboard input, so let's enter a test definition. I'll make a deliberate typo to check if backspace works. Do test 1, get it to print out the value 10. Notice that I've pressed enter, but there's no OK prompt, and this is because our new word is handling all the input, not the interpreter. I'll do one more, test 2, this will display 20. Right, let's say this is all we want to enter, and press escape to finish, and take a quick peek at the buffer. 60,000, and then fetch character and demit it. There's the colon, as we'd expect. 60,001 is a space, and 60,002 is the T. This looks promising, so let's check the end of the line at offset. If you count, it's offset 14. So 60,014, and we won't emit this because it's a control key, so we'll do a dot or print to see the ASCII code, and it's a 10, which is a new line. Same again for the screen terminator. Each line is 14 characters plus the new line makes 15. 2 15s is 30. So if we look at 60,030, it's 255, which is as we'd expect. Okay, now for a routine to display the buffer contents properly. This is just for confirmation at the moment, but the target editor will need something like this to present the screen for editing. So first a couple of support routines like before. I won't go into the details, but there's a get character and a display character. And then the main display routine called display screen clears the screen, puts the memory address on the stack, gets a character, and displays it. And it keeps looping round until it hits the end of the screen terminator. Okay, let's see what we've got. Display screen. And these are the previous test definitions we entered earlier. Let's just confirm there are no test words in the dictionary. Test 1, test 2, not found. But if we use key source to read and parse the buffer contents, say the screen address, I'll use a non-zero value here, which tells key source to echo what it's reading. Then we should now have two new words in the dictionary. Let's try them. Test 1, there's the value 10. Test 2, value 20. Okay, the next word is to write the buffer to disk. I'm going to be using EDS1 for this. So I'll define the drive number, drive 1. Now the disk drive is asynchronous, so we need to check its status before use. I'll define some support words to make this easier. Now the spec says that set sector number is ignored if the drive status is off, in other words no disk is loaded, or if the status is busy. So we'll put those status values here. Status off is a 0. Status busy is a 2. And now a word that says wait for drive to be on. Wait on. Put the drive number. EDS stat is a system word which means get the status for that drive, and it will put the value on the stack, and we're going to compare it with status off. If it's true, the value will be non-zero, and we're going to jump back to do the test again, which if you count 2, 4, 6, 8, 10. So it will wait in this routine until the drive is on. End. Same again for wait if not busy. We put the drive, EDS status, and this time we're going to compare it with, run off the page, status busy, and if it is busy, jump back -10. Now we can use the set sector number, and it's just going to call these words wait if on, or wait until on, rather, wait until not busy. And then we want to set the sector number. Now this routine is going to assume that the 16-bit sector number is on stack. Sector numbers are 32 bits, but I'm not going to bother with the most significant for this first example. So we'll put the most significant bit on stack, the 0, and then we can say drive EDS set sector number. End. So this is another system routine which takes the top two values as a 32-bit quantity and sets a sector number for that disk drive. So we can check this before we move on. Disk is unloaded. Let's try setting sector 5. 5 set SN. It's waiting for the drive to be on, or the disk to be loaded, so let's load it. It's dropped out, so we'll assume it's done it. We can confirm it by reading the sector number from the disk, which is EDS get sector number. And we'll print the two values, and there it is, 5. Now the write sector function just needs to wait until the drive is ready. So we'll do a similar trick. We'll just say status ready from the spec is a value 1, and a routine that says wait ready drive number EDS status, and we'll compare it with status ready. And if it's not, it jumps back -10. And now we can make a write sector routine. Write sector, which will have an address on the stack, and it will wait ready, and then just call the system routine EDS write, and that will write the contents of memory starting at this address and write to the sector that we selected with set sector number. The read sector function is similar, except that we have to request the sector first and then wait for data ready before getting it. So I'll have a status data ready, which from the spec is the value 4, and now wait for data ready, drive EDS status, and compare it with data ready. If it's not data ready, jump back. Now these routines don't check any other status values like errors, but that just makes it more complex, which we can do without for now. Right, now for the read sector routine. Read sector, again that's going to take an address on the stack, that's the memory buffer. It's going to wait for the drive to be ready, and when it is, we do an EDS request, and then wait for data ready and an EDS get. And that fetches the contents of the sector and puts it into memory at this address. Right, I'm just going to enter these routines. Okay, so how do we map a screen's worth of data onto disk sectors? Well, there are several ways. I'm going to keep it simple and just allocate a fixed number of sectors for each screen. So we'll have a screen which will have so many lines of forth on it, and we're going to write that to a set of sectors on the disk. And I'll always have a fixed set no matter how many lines are on the screen. A bit inefficient, but it will do for now. So how many sectors do we need for the worst case scenario when the screen is completely full? Let's define a word that will do that. Screen size. We can use some more system calls. It's the number of columns by the number of rows. So there's a convenient TTY cols. But we want to allow for the new line at the end of each line. So we'll add a 1 to it. And then we'll multiply by the number of rows. TT2I rows, multiply, and then the extra character right at the end, the screen terminator, we'll add another 1. So that's the total number of characters for a full screen. I mean, in the target, these lines might be numbered. I don't know yet, but this is the worst case. So let's check it. And there's the value 667. And the disk sector size is available from the EDS info word. So let's do sector size. And we're going to wait for the disk to be on and then call EDS info, and that returns the size on stack. So let's check it. Sector size dot 128. Right, now for a calculation, which you could probably do in your head, but let's do it using forth to see how many sectors we need to store a screen. So sectors per screen, so we divide one by the other, but we want to round it up. So we'll do screen size, we'll add a sector size first, and then we'll divide it by sector size. So that will round up the value. Let's check it. Sectors per screen, print, and it's 6. Right, now for the main read screen and write screen words. And as before, I've been through a few iterations on paper and I've factored out some common code. They might not be the best named words, but I got one called prep sector, and it takes a screen number on stack and it returns an address and a sector count, how many sectors it needs to write. So to convert the screen number to the sector number, we multiply by 6, or more generally, multiply by sectors per screen. So that will give us the sector number on stack. And we can now call set sector number with that value and pop a couple of start counters on the stack. There's the memory address start value and the number of sectors per screen. And it's going to increment the address and decrement this value until it reaches 0. So that's the prep word, and then the other word I've got next sector, which takes the sector count, the address, and returns an incremented address and a decremented sector counter duplicated. This might be messier than it needs to be, but that's how I've done it. So we're going to increment the address by sector size. So that will leave us S and A+. I'm going to swap these over, and so that's A+ and S, and we're going to decrement the sector count. So this is A+, that's minus, and need to duplicate, and that's the end. Okay, the main write routine is now write screen expects a screen number on the stack. It's going to do prep sector, swap, dupe, write sector, and then the other support routine, next sector, which adjusts all the counters, and it keeps jumping round the loop until the sector count gets down to 0. We're going 2, 4, 6, 8, 10. We're going back to here. And when we're finished, there are 2 items on the stack which we're going to drop, and that's it. So let's check this. We go for screen 0 and then write screen. You should see the disk write light flash, and we'll need to check the contents later. Right, the read routine is exactly the same, but it calls read sector instead. So we want read sector, swap, duplicate, and read sector this time. So write sector, exactly the same. Next sector, 0. Okay, we can check this now. We'll go screen 0 again, read screen, and you should see the read light flash. We could try key source now to execute the disk contents directly, but I'll be showing that later. Right, now for the real test, I need to create and save screens for all the definitions which constitute phase 1, which basically means typing all this lot in again, but this time using the new screen word to capture them and write screen to save them. And if I mess up, I can undo simple typos with the backspace key, but if there's anything more serious, I'll have to abort that screen and re-enter it. So I'll try not to cram too much onto each screen. They can always be reorganized later. So here goes. Okay, that will do for this screen. Press escape to terminate and write it to disk as screen 0. So 0 write screen. an encouraging sound. Okay, on with the next one. New screen, and enter the data. Do escape, and this time screen is 1, right screen, and we'll kick off a new screen straight away and carry on. Okay, escape, screen 2, right screen, new screen, escape, screen 3, right screen, new screen, escape, 4, right screen, new screen, and finally escape, and 5, right screen, and that's it. Phew. All 6 screens, 0 to 5, are now saved, I hope. Let's switch off and see if we can load them back. The power off, power on, load the microcode, load the disk. Okay, confirm there's no read screen word or no wait key word in the dictionary. Use key source to execute direct from disk. I'll start with sector 0, but it's already 0 when the disk is loaded, so I don't need to do anything. And we should see what it's loading from disk. Now let's see if we have a wait key word. Wait key emit. Perfect. And the first screen occupied sectors 0 to 5, so the next one starts at sector 6. I need to check the drive status before setting the sector number, but there are no disk handling words yet because we've not loaded them, so I need to do this manually. And there's no drive value either. I need to put this in 1 for EDS1, EDS stat, and print it. And the status is 1, which means ready. Okay, now the 32-bit value for the sector number. The LS part first, 6, then the MS part 0, drive 1, EDS set sector number. And now I can read from that point using key source as before. Device is 5, put echo on, key source. Okay, now we have the drive handling words, so I can use these from now on to change the sector number. Let's define a load word to automate this for any screen number. All I need to do is convert the screen number to the sector number by multiplying by 6, set the sector number, and then use key source to read and parse that item on the disk. Let's try it. Screen 2, load, screen 3, load, and so on. Now this could all be improved later, but we should now be back to the state before we switched off. So let's try reading a screen and displaying it. screen 0, read screen, and display screen. Perfect. I can now shunt these around and create more screens and so on, and develop the application further. Okay, that's it. Maybe not the best guide to writing forth, but it works for me. And it was very satisfying to get a result so easily with just a few simple words. And even at this low level, it's so much easier than entering binary on the switches. And if it's encouraged anyone else to dip a toe in the water instead of passing it by, it's been worth it. So thanks for watching.